Hey guys, we're now going to look into a type of projectile motion problem where you launch something up at an angle and then it lands below your original height. So something like this. Your final height is below your original height. All right? So I call this launch up from a height, not very creative. So in these problems, the first part of the motion is symmetric. And what I mean by first part is from A to C. Remember, if two heights are in the same, if 2 points are at the same height, they're symmetric. That means that the time to go up is the same as the time to go down. So by first part, I mean A to C. But the object drops further. Drops further is C to D, this piece over here. And that's what's different between this type of problem and, let's say, symmetric launch problem. Okay, so when we're solving these problems, there's three legs here: A, B, B, C, and C, D. So we're gonna get to pick intervals for some of the things we're solving for, and whenever possible, we're gonna try to include point B in our intervals. Okay, so if you have a choice of intervals, sometimes you do, sometimes you don't. We're gonna try to include point B, and I'll show you this in this example. Point B is simply the highest point, the max height. And the reason we want to include this is because the velocity at point B in the y-axis is 0, which means our equations will simplify. They'll be a little bit simpler, they'll have one less term, and that's good news. So I'll show you how that works. Let's go ahead and do this problem. And here it says you throw an object from the top of a 100-meter tall building. So this is 100 meters. With 50 meters per second, so VA equals 50. At an angle of 37 degrees above the x-axis. So that's this. I'm going to call this theta A equals 37. Now the first thing I'm going to do here is actually decompose VA into VAX and VAY. So VAX is, which by the way, VAX looks like this, is simply going to be my Vx because the velocity in the x-axis, remember, stays the same always. So VAX, the same as Vx. It is VA cosine of theta A, and you get 50 cosine of 37, which is 40. It's positive because it's going to the right, so that makes sense that you get a positive out of 40 here. VAY is VA sine of theta, so 50 sine of 37, which is a 30 meters per second. So VAY is 30, and it's a positive 30 because it's going up. We don't have a lot of space, so I'm going to try to compress all the information here. Cool, so that's the first thing we do, just split that up real quick. Now let's see what they're asking us. They're asking us for the maximum height. As you look through your 5 variables of motion, you should identify that the maximum height has to do with your delta y. But it's not just your delta y, let's say from A to B, but instead it is this original height here, 100 meters, plus the height from A to B. That's your total maximum height. Okay, so your maximum height will be 100 plus this length here, which is your delta y from A to B. I have the 100 obviously, but I don't have the delta y, so that's what I'm going to get. Once we have the delta y, we'll have the final answer for the maximum height. So that's what we have to do. Let's go find delta y between A and B. Now remember, for every question you're asked, for every variable you're looking for, you have to go through the steps, determine the axis, right? So delta y is obviously the y-axis. Pick an interval. Well, if I'm looking for delta y from A to B, the interval is already picked for me. It's going to be A to B. And pick an equation. That part you do have to do. So to make this a little bit simpler, rather than work with the entire picture, I'm going to sort of cut out just this part, just the y-axis from A to B. Okay, so I'm going to draw what the y-axis from A to B would look like. And again, on the y-axis, you're either going up or down. In this case, from A to B, I'm going up, A to B. The initial velocity here is VAY, which is 30. And the final velocity here, VBY, is 0, because that's what happens at the maximum height, right? VBY over here is 0. What else do I have? I'm looking for delta y for this interval. The other two variables are delta t, I don't have delta t, and acceleration. Acceleration is gravity, but it's negative because it's going down. And remember that going up is positive and going to the right is positive. That's what we're going to use as a standard. Delta y is going up, so it should get a positive. This velocity is going up, so this is a positive. And I don't know time, but that's okay because I already know 3 out of 5 variables. So time is simply my ignored variable, but I'm still able to find delta y. Since time is my ignored variable, that means that I'm going to use the second equation to solve this. So the final velocity squared equals the initial velocity squared plus 2a delta x. But we're in the y-axis, and the final velocity in the y-axis is 0. The initial velocity in the y-axis is 30. The acceleration is negative 9.8. And delta y is what I'm looking for. Okay? And if you move things out of the way, you get that, move things around to solve for delta y, you get that delta y is 45.9. I'm going to round this to 46 meters. So delta y is 46 meters. But remember, delta y is not what I was looking for. I was looking for delta y so I can plug it in here. And what I was actually looking for is the final, the maximum height, which is 146 meters. So that is actually my final answer right here. Maximum height is 146. Delta y is just the step in between. Now the next part, so that's part A. Next part is asking for the time to reach the maximum height. So the time to reach the maximum height. So that's delta t. And again, to reach the maximum height, that's A to B. So the interval is already picked out for me, A to B. Now, what's special about time is that time could belong to either the x-axis or the y-axis. And typically, I would start with the x-axis, but I'm gonna just advance you, let you know that if you try the x-axis, it's not gonna work. So I'm gonna just jump into the y-axis. And actually, if I'm looking for time from A to B, all it is this guy right here, what used to be my ignored variable. Now we can solve for it. All right. So, except that now I actually already know 4 things about this motion, which means I'll be able to pick not just one equation but 2 equations. So we'll pick the simplest one. All right. In this case, I can use the first equation, and v final equals v initial plus a t. The final velocity, we're talking about the y-axis as it go up. The final velocity is 0. The initial velocity is 30. The acceleration is negative 9.8 t. And if you move things around, you get that t is 3.06 seconds. All right. And this is the answer to part B. That time is 3.06 seconds. All right. So part C asks for the total range. And we call that, another word for that, another term for that is horizontal displacement. That's just your delta x. So let me do this over here. I'm looking for delta x. Obviously, delta x is an x-axis variable. And the good thing about the x-axis, again, there's only one equation. So let's write that. And it says delta x equals vx t. Vx is always the same. In this case, it's 40 t. Okay? Now, I don't have t because if you're careful here, this delta x is actually the entire, right, the total range, the entire range from A all the way to D. So if I want delta x from A to D, Vx is always the same, but I need to use the time from A to D. And I don't have the entire time from A to D, I just have the time going up. So that's what we're gonna have to find first, okay? So I'm gonna have to first find what is delta t from A to D, and then I'll be able to plug it back in here. In doing this, I am already determining that the interval is going to be from A to D, and since I just got stuck in the x-axis, we're going to do this in the y-axis. Okay, so I'm going to move over here and find what is the total time in the y-axis. Actually, let me do a little bit more work here. The time in the y-axis from A to D. Again, the time is the x-axis or y-axis, doesn't matter. But we're solving this in the y-axis. You could think of this as the time to go from A to B plus the time to go from B to C plus the time to go from C to D. And if you look closely, you have this first time 3.06, but if you know that it takes 3.06 to go up, you know that it also takes 3.06 to go back down from B to C, right? You know that this time here is also 3.06, right? So you actually know both of these. One way you could do this is just finding the time between C and D, right? Just write a little interval diagram from here to here and find the time in the y-axis. The thing is, it turns out that if you go from B to D, it's actually easier, and it's the point that I made in the beginning, that as much as possible we're going to try to include point B, because things will simplify. Okay, so we're gonna, instead of thinking of it as A, B, B, C, and C, D, I actually want you to think of time total, any kind of time total, as simply the entire time up plus the entire time down. In other words, this is AB and this is BD. And if you do it this way, notice that this guy has a B in it and this guy has a B in it, and that is better. So I want to use the entire time to fall. Okay, I already know this, so this is actually what I need. So let me go over here to the side and find what is the time delta t from B to D. And again, we're going to do this in the y-axis because we're stuck in the x over here pending what we find in the y-axis. Okay, so that means I'm going to draw a little diagram from B passes C, D down here, and we're going to plug in all the information we know. This is in the y-axis. The initial velocity is VBY, and that's 0 because it's the highest point. The whole reason why we're doing this from B to D is because we want this to be, one of these numbers to be 0. This is VDY, which I don't know. The time is what I'm looking for. The acceleration is gravity. Now it's negative gravity, negative 9.8 because it's going down. What else? The fifth variable here is delta y. We do have this, but you have to be careful. If I'm going from B all the way to D, I have to use the entire height, which is not 46. Remember, this is 46 over here. You don't use the 46, you don't use the 100, but you use 146, the entire thing. And you're falling, so it's negative 146 because you're going down, and going down is negative. So if you look around, you know 3 out of 5 things, and this is your ignored variable. So I'm going to use the third equation to figure this out, right? So let's use the third equation here. The delta x equals v initial t plus half of at squared. Delta x is actually delta y, which is negative 146. This is 0 because we're talking about the velocity initial in the y-axis. That was 0. This is half negative 9.8 t squared. Okay, and then if I move some things around and I solve for t, I get t equals the square root of some stuff. And if you plug that into the calculator, you get 5.46 seconds. Okay, 5.46 seconds. That's not the final answer. That's just what we have for now. Let me make a quick point here. Notice how you're looking for time and this guy canceled here. It canceled because we're going from B to D, and the velocity at B, this is VBY, is 0. If we were going from C to D, this guy would not have canceled, and I would have to use the quadratic equation to solve this, which sucks, right? So we want to avoid that as much as possible. So we want to include the point B. Cool. So I got this time, and I needed this because this time is actually this guy over here. So time total is 3.06 plus 5.46, and I have this here. The total time is 8.52 seconds. Now, all of this, we weren't actually directly looking for the total time. All of this is so that we can plug this total time in here. Okay? Delta x total, let's wrap this up. Delta x total is Vx, which is 40, times the entire time, 8.52. And if you do this, you get, this rounds to 341 meters. Okay, so this question is long and tricky because it asks for your total delta x. It never asked you for the total delta t, but you had to go get it. Okay, so that is part C. Make a little space here. And now we're going to go to part D. Part D asks for the magnitude and direction of the velocities at point B, C, and D. Okay, so first VB. Remember, vector, the velocity vector is tangent to the path, so it looks kind of like this. So at VB, which is your highest point, VBY is always going to be 0. And VBX, remember, the velocity in the x-axis never changes, so VBX, just Vx. It started at 40, continues at 40. If I want VB, I need to have VBX and VBY. Every vector, for you to find the magnitude of a vector, you have to know its components. And then I can just do the Pythagorean theorem with the components. Here, notice what happens. My VBY is 0, so VB is really just VBX, which is 40. Okay? That happens because this vector is entirely in the horizontal axis. It has no y component, right? It's flat in the x-axis. So the entire vector is the velocity in the x-axis. And because of that, theta is simply 0. Now, if you want to verify that, you could have done that theta at B is the arctangent of y over x, so 0 over 40, and that would have been 0. But just by looking at the diagram, you can see that. And the velocity, the angle for the highest point of the velocity at the highest point will always be 0 because it's always going to look like that. Okay? Now let's look at VC. Again, to find VC, I'm going to need VCX and VCY. VCX never changes. It's a 40. Now VCY, Y is a point that is symmetric to A. So if my velocity going up, VAY is 30, my VCY is negative 30. Okay? So VCY is negative 30 because of symmetry. And I can now, having these two numbers, I can now get my VC, which is going to be these two. So 40 squared plus negative 30 squared. And you get a 50 meters per second. If you do the arctangent, theta c, arctangent of VCY, 30 over 40, you get a negative 37 degrees. These numbers, again, shouldn't be a surprise. These numbers are the same as these numbers here, okay, except that the angle is different. The magnitude of VC is always going to be the same as the magnitude of VA if A and C are symmetric, and the angle of C is always going to be the negative of the angle of A if those 2 points are symmetric. And that's because the sides, the legs of the vector are the same, right? They just flipped. This is my X, this is my Y, and then at point C, it does this, and just the vector over here just flips down instead of up. But the magnitudes are the same, so we actually didn't have to calculate anything. VD is going to be a little bit more complicated. VDX is 40, but I do have to find VDY to be able to do this. Okay, so we don't have VDY, we're going to have to go get VDY. And again, if you want VDY, which is this velocity down here, right, VDY, you have to write an equation. You know, pick an interval, write an equation, and the best interval here is going to be, again, not C to D. I know that this is 30, so maybe I could just go from 30 and then figure out what D is, but it's actually better to use B all the way down to D. Once again, we want to involve B as much as possible. That's one reason to do it, because B, the velocity at B is 0, but also because we already drew this over here and we have a bunch of numbers already kind of worked out. In fact, we already know 4 things about this at this interval. I already know that this time is 5.46. So I'll have a greater selection of equations, if you will. So let's go and look for VDY, which is this guy over here. Okay, so I'm going to go over here and find VDY. I can simply use the first equation, and v final equals v initial plus at. We're on the y-axis, and the initial velocity there is 0. And I can just plug in these numbers, negative 9.8. The time I have to use is the time for this interval, so it's 5.46, not any of the other times. And if you do this, you get, I have it here somewhere, 53.5, negative 53.5 meters per second. It should make sense that it's negative because this thing is going down, so we expect that it would be negative. Okay, so now I know that this is negative 53.5 right here, and I can just do VD Pythagorean and if you plug this, you get 66.8. And if you do the angle, the arctangent of y, negative 53.5 over x 40, you get 53.2 degrees, negative 53.2 degrees. And let me clean this up a little bit. And that is the correct angle, because VDY over here, once again, you're going this way. This is your VD. You are in the fourth quadrant, so you don't have to touch up the angle. The angle is the correct one coming from the arctangent. All right. So these are all the numbers. VB is 40, theta B is 0, VC, for some reason I changed colors here, and then VD are these. All right. So I know this was a long example, but this sort of helps me explain all the little details about these kinds of problems. There's one more thing that I want to show you. So it says here, if we're answering multiple questions like we just did, you go from A to B and then B to D, and you do all kinds of different things. It's often easiest or best to break up the motion. So in this case, I did AB, and then we did BD. And once again, notice how that ends up B being part of both, and that's good. Usually that's what you want to do. You have to break it up because you have to find parts of it anyway. But if I'm only asking you for one thing, or in some other situations, sometimes it is better or easier or faster, whatever the situation, to actually just solve this in a single step, going from A to D. And that's what I want to show you real quick, so you know that you can do this. Here we're going to throw a rock from a 60-meter cliff. So let's make a tiny little cliff here, 60 meter. We're going to throw this rock with 50. So call this VA equals 50 at an angle of theta A equals 53 above the x-axis. And obviously this thing is going to go and land over here somewhere. I'm going to call this A, B, C, which in this case is not important, and D. All right. And I want to find the vertical component of the velocity at point D. So VDY. What is VDY? And I want to do this in a single step. Okay. So let's do that real quick. So I'm looking for a velocity on the y-axis, so I'm going to use a y equation, a y diagram, and I want to go from A all the way to D in one shot. So let's draw what's happening on the y-axis here from A to D. You're going from A, you go up to B, and then back down to D. Okay? And there's B here, and there's C here. Now, if I'm going to do this in one shot, I'm going to have to pick one equation and do it. But it's going to be easier if I actually list my variables real quick. I have my initial velocity, which in this case, my velocity at a y, which I have to find by decomposing. And then I have my, that's my initial velocity right there. And then I have my final velocity, which is my velocity at point D, VDY, which is what we're looking for. Okay. Then there's the acceleration, which is gravity, negative 9.8, because we're going down. Then there's the amount of time that it takes, delta t. And then there is the height. So I can find VAY. Let me do that real quick. VAX equals 50 cosine of 53 which is 30. This is just my Vx throughout. And my Vy or Vay is 50 sine of 53, which is 40. So this initial velocity here is 40 up, so it's 40 positive. Okay, now I'm looking for this variable, which means I need to know three others. I have 1, 2. The third variable is going to have to be either time or height. If you look at question B, it's asking for the total time of flight, so I'm probably not supposed to have that just yet. Do I have delta y? I do. Now this is where it's a little tricky because I am on top of a 60-meter hill and I go up and then back down. But the way to approach this is to look at the very beginning and then the very end. Forget what happens in the middle. And if you look at the very beginning, I start here. The very end, I go here. So effectively what's happening is I'm going this way. Beginning to end, forget what happens in between, I'm going down. So I can say that my net delta y is that I'm actually beginning to end falling 60 meters, right? Again, forget the middle. I'm falling 60 meters from the very beginning to the very end, so it's negative because it's going down. That is my third variable, and I can now use delta t as my ignored variable, and I can now use my second equation to get our final velocity, which is this variable here. Okay, so the final velocity is the initial velocity, 40 squared, plus 2, negative 9.8, and then instead of delta x, it's actually delta y, which is negative 60. Okay, and if you plug in all these numbers and you carefully solve for v, you get that v is the square root of some stuff. This is your final velocity, which is, I have it here, you get a 52.7 meters per second. But be careful, when you're coming back down, your velocity, vdy, is going down, so it should be negative. So I'm going to put a negative in front of here. Remember, when you take the square root of a number, for example, square root of 9, you really get a plus or minus 3, because 3 squared equals 9, and negative 3 squared equals 9, which means you can just add this negative here, and you're not violating any crazy rule, right? So that is part A, that the final velocity on the y-axis, v dy, is negative 52.7, and I did that in one shot. I didn't go up and then back down, did that in one shot. All right, now let's do part B. Let's try to squeeze part B over here. What is the total time of flight? So again, in one shot, so it's the same interval from A to B, and here I can just use the first equation, v final equals v initial plus at. V final, again, in the y-axis, we're going up and down, so it's v dy, v initial is vay, and the acceleration is negative gravity, and time is what I'm looking for. The final velocity in the y-axis, I have it right here, we just got it, negative 52.7. The initial velocity in the y-axis was 40 minus 9.8 t. And if I shuffle everything around, I get that t equals 9.46, roughly 9.46 seconds is my total time. Okay, so we just did two questions in two very different ways. One of them asked for a lot of stuff, so we broke it up. And that's usually what you're going to do most of the time, because these questions are usually going to ask you for a lot of things. But in some cases, you might want to just do it in one step and get it out of the way quicker. All right, so that's it for this one.